Chapter 6, Parallel Circuits. A parallel circuit is described as where each and every load in the circuit shares the same two terminals of the source. So that means in the circuit that we see here with 3 lamps, notice how the source positive terminal is extended out here, the negative terminal is extended out here, and each and every load is connected to those 2 terminals. And so this is where we say that defining a parallel circuit is where each and every load is connected or sharing the same 2 terminals of the source. So that being said, for a parallel circuit, because every load is connected to the source or connected to the voltage, we can say that for a parallel circuit, VL1 equals VL2 equals VL3, where each one of these lamps is L1, L2, and L3. And so in a series circuit, we had current as the common quantity. In parallel, we have voltage as the common quantity. When we're looking at each one of these lamps, let's say this one is 100 watts. Let's say this is 40 watts, and this is 60 watt lamp. With each one of these lamps, it's doing a different amount of work. It's dissipating a different amount of power, but we know the voltage is the same for each one. We know that P is equal to V times I. And so if voltage is the same for each one of these lamps, we know the quantity that's going to be varying between each one of these is the current, right? So current is going to be what is changing in this arrangement for each one of these loads. And so if we were to consider the current of lamp 1, leaving also the source is the current for lamp 2. Leaving is the current for lamp 3. And if that's the case, then instead of a voltage divider like what we had in the series circuit where the total E total value is being divided by the loads, in this case we have I total being divided by the loads such that I total equals I1 plus I2 plus I3. So this is where a purely parallel circuit is called a current divider. So house circuits are in parallel. And the idea behind parallel connections is such that each and every load can dissipate its full rated power because it's connected to a specified source voltage. In this case, maybe this is a 24 volt source. Each and every load is connected to that source, is rated for 24 volts as a voltage rating so that it can dissipate its rated amount of work, or 100 watts, 40 watts, 60 watts in this case. It also provides independent operation of the loads. So what it means is that if we were to put a control device or a switch into each one of these branches, we could independently control the 100 watt, the 40 watt, and the 60 watt. An example of a series connection of where there is not this independent control would be those old Christmas lights, where if one of the lights in the string were to burn open or go open circuit, all the rest would be disabled. You'd have no light on the whole string until you found the open circuit bulb and replaced it such that there was continuity in the series loop. You can see how inconvenient that is. You can see how it's not practical. And so a practical connection for circuits is a parallel circuit example of where you can independently control the loads. So you can imagine if this 40 watt were to go open, that would mean there'd be no longer an I2 component to our total current, but there's no doubt that I1 and I3, or lamp 1 and lamp 3, would continue to draw current from the source because they share those source terminals, and they would continue to dissipate 100 watts and 60 watts respectively. One load had no effect on the other load, giving it independent operation. So it doesn't matter how circuits are drawn, the way we evaluate their connection is by following the nodes or the connections that make up the circuit. And so don't be fooled when you see examples both from the textbook and other drawings that maybe don't look traditionally like a parallel circuit. But if we were to look here, we could see that for both load A and load B, it has a connection to this side of the source for each one and a connection to this side of the source for node B. That makes that a parallel circuit. So it doesn't matter how things are drawn. Take a look at this one. When we look at evaluating each and every load sharing the same two terminals of the source, if I was to mark this positive and it's negative, you can see that even though of its odd shape and its odd drawing, that is also a parallel circuit. So this is a parallel as well. So follow the connections to determine or evaluate how a circuit is connected, regardless of the way it's drawn. So as we've studied series circuits now, we need to be able to identify both series and parallel connections. Obviously, when we get to a combination circuit like what we see here, we have to look at parallel components and series components and then apply the properties for each connection. So how would we describe the one that we see here as A? We would describe it as the load A is in series with the parallel combination of B and C. Load A is in series with the parallel combination of B and C. So if we were to then just say, okay, we have an E total value here, and for sake of understanding, we'll give it polarity. If we were to write essentially some equations that we know would be true based on what we know now, what are some of the things we could say? Well, one of them is we know that a series connection makes a voltage divider. So therefore, making a voltage divider, we could say that E total equals VA plus VB. Or E total equals VA plus VC. And part of that is knowing that because parallel connections share the same voltage, that VB equals VC. Taking that a step further, if we talked about current here, we can see that the full circuit current is flowing through component A and then being divided at this node A, and we have IB and IC. So if we look at the current entering that node and the current exiting that node, we could say that IA equals IB plus IC. Okay, looking at this one over here on the right, how would we describe it? We would say that the load A is in parallel with the series connection of B and C. Load A is in parallel with the series connection of load B and C. So how could we describe voltage in this case? We could say, as an example, that VA would equal VB plus VC. B and C are a voltage divider because it's in series, dividing what voltage? The parallel voltage. And the parallel voltage is voltage A. So voltage A equals VB plus VC. What else could we say? We could say that the total current, if we labeled this total current here, we could say that IT equals IA plus IB, or I total equals IA plus IC. And that, of course, is based on what we know about series, where the current is the same in a series connection. So that means this comes from the IB equaling IC of that series connection. So that's just a little bit of a going forward as to how we apply these principles and rules for both series and parallel to combination circuits. So when two or more components are connected across each other and share the same voltage source, they form a parallel circuit. So that's what we see here. R1 is in parallel with R2, is in parallel with R3. And I just want to talk about a new kind of symbol or way of indicating our opposition equation for parallel. So first of all, if we were to look at quickly just a series circuit where this is R total and we have three resistors in series, R1, R2, R3, our opposition equation would simply be expressed as R total equals R1 plus R2 plus R3. That would be our opposition equation. How do we represent that here? Well, this is the way this is represented for parallel. R1 in parallel with R2 in parallel with R3. So this is a way of symbolizing a parallel connection. So you'll see this in your textbook, you'll see it in labs, you'll see it in curriculum, and the parallel lines are indicating that the connection is parallel. And so you have to know how to process that to determine total opposition. So when it comes to parallel resistance, we have an equation that looks like this. R total equals the sum of 1 over R1 plus 1 over R2 plus 1 over R3, and then you take the reciprocal of that sum. So once you've determined this sum, you would take the reciprocal or the inverse of that sum. Now, what does that really come from? Well, one quantity we haven't looked at before is one called conductance. So conductance is the exact opposite of resistance, and it's symbolized by the letter G. So G equals 1 over R. It's the reciprocal or opposite of resistance. So the less something resists, the more it conducts. The more something conducts, the less it resists, and so on. So if you were to think of representing each one of these conductances as resistance, you would have G total equals 1 over R total. G1 equals 1 over R1, G2 equals 1 over R2, and G3 equals 1 over R3. Knowing that then, and knowing that every time we add another branch, we've added more conductance. So if we think of the conductance evaluated by one branch, it's conducting at a level of X. If we were to add another branch, it's conducting more. There's more conductance going on each time we add another branch. And so the equation for conductance here then would be G total equals G1 plus G2 plus G3. But now what if we wanted to evaluate that for conductance, or I mean for resistance? If we wanted to evaluate that for resistance, then remember G total is 1 over R total. G1 is 1 over R1. Okay, you get the idea. Now, if I want to make all of this representing R total on its own, I have to take all of what I have there and put it 1 over. All we did was transpose this equation to give us that. So that's one way of looking at it in terms of conductance, a variable that we haven't talked about, a quantity we haven't talked about, that is simply the opposite of resistance. So that's going to give us this equation. And one important note here to help you sort of verify that you have the right value is a quick check to make sure that the total resistance of any parallel circuit is less than the smallest individual resistance value. So what do we mean by that? Let's say we had parallel resistance of 10 ohms, 20 ohms, and 30 ohms. We know that to, first of all, predict our resistance, we know that the R total would have to be less than the smallest individual value, and in this case would have to be less than 10 ohms. When we're done, the result would have to be less than 10 ohms. So if we take this example here and label each resistance, we've got 33K, we've got 56K, and we've got 10K. It says to calculate the total resistance, and we know that based on the smallest individual value being 10K, when we're done this calculation, the result should be less than 10K. So remember, our total equals 1 over R1 plus 1 over R2 plus 1 over R3. So if you want to get out your calculator and check that or verify it, when you're done, you know the result should be less than 10K. So if we look here at processing that, we see that we have a value total of 6.75K. 6.75K, and the resistance, you can see, is clearly less than the smallest individual value, the smallest being 10K. All right, so remember we talked about these parallel lines here indicating our opposition equation for parallel. So that's what we see here. R total is equal to R1 in parallel with R2 in parallel with R3. When resistors are equal, that means they conduct an equal amount of current. So if we were to evaluate that here, we know this is a current divider. We know that we've got the same 50 volt source connected to each one of them. That means that each current will be identical. Ohm's law says that 50 volts divided by 12K for each branch means that I1 will equal I2 will equal I3. That doesn't sound like a property of a parallel circuit, because that looks like a property of a series circuit where current is the same for all loads. But in this case, it just happens to be the same because the resistance is all the same. So with voltage all the same and resistance all the same, the currents are going to be all the same. And therefore, it means that our total value can be found by taking the value of resistance of a single resistor and dividing it by the number of resistors. So notice we've got 3 resistors, each of them 12K. What will the total resistance be? 12K divided by 3 equals 4K. Notice that every time you were to add another resistor, the resistance goes down. What would only 2 resistors be? Our total now would be 12K divided by only 2 resistors to give you 6K. Notice how adding a third one dropped the resistance even more. And why is that? Because the conductance went up. So if we were to look at this, then let's figure out individual currents, add them together, and then see if we can confirm that 4K. So we would start by I1 equals 50 volts divided by 12K. And then we know that I1 equals I2 equals I3. Okay, so I got my calculator now, so we'll just take 50 volts and divide it by 12 exponent 3, giving us 4.17 milliamps. So that means that I1 equals 4.17 milliamps. And we know that we now have three currents that are identical. So we can just determine the total current by adding them all together. So that'd be 4.17 plus 4.17 plus 4.17 to give us our total milliamps of 12.51. So now that means that our I1 plus I2, plus I3 would equal 12.51 milliamps. And now we can divide R total equals E total divided by I total. E total in this case was 50 volts. I total is 12.51 milliamps. So now we'll do the division. 50 divided by 12.51 exponent minus 3. The result is 4K ohms, which is what we got here. Okay, so what are we taking away from this? These are ground connections, by the way, guys. So we know that grounds are often used to show a simplification of the circuit and reduce the number of lines and intersecting lines in a schematic. But no doubt you could simply connect all of these points together as a common point to give you a closed loop. So you can see how in this case we went through the same process. For some reason we're missing equal signs in this in these slides when I bring them up on my iPad, but that's what we have here is what we calculated. So when it comes to working with parallel resistance, there's some shortcuts we can use a lot of times based on some of the rules that are around parallel connections. And one of them that's easily used and often used in circuit analysis is something called product over sum, and it's for two resistors in parallel. Now there is product over sum equations for resistors all the way up to infinity in parallel, but the thing is it really loses its advantage for anything really, I would say, beyond 3 or 4 parallel loads. If we look at the equations for even a 3 parallel resistance, the equation becomes far more involved. So it's used often to do a prediction of parallel resistance, even just in your head, without having to find a calculator or whatever. And it's simply this: R total equals R1 as the product over the sum. So it's adding R1 to R2. So if we look at applying that to any circuit, let's go back here and let's just say we have 10 ohms in parallel with 20 ohms. and we want to know the R total value. Well, we can say 10 times 20 over 10 plus 20 is going to give us the result. So that's 200 divided by 30, giving us 6.67 ohms. And so that's the result of product over sum. And notice how the total resistance is less than the smallest, which was 10 ohms. What would that mean if we were actually looking at 3 resistors and we had 30 ohms in parallel yet still here to consider? Well, it doesn't mean with product over sum that we're out of luck when it comes to 3, because what it means is we can look at the parallel resistance that we determined for these 2 resistors and this as that equivalent value, and now just use product over sum once again. So it means that we could say 6.67 ohms times, as a product, 30 ohms over 6.67 ohms plus 30 ohms. We're just going to be applying product over sum again, carrying on through to give us the result. So that's going to be 6.67 times 30 divided by 6.67 plus 30 to give us a total of 5.46 ohms. Again, you can see 5.46 is less than the smallest individual resistance value of 6.67 ohms. So product over sum, we use it lots when we're coming up with parallel values, both in AC and in DC. So as we said, we know that voltage is the common quantity in a parallel arrangement. So that means all the values of voltage of the individual loads, because they share the same 2 terminals of the source, will always be equal to the source voltage. We have Kirchhoff's current law then. It states that the sum of all currents entering a point or a junction must equal the algebraic sum of the current leaving that junction. So that's just like we said for voltages in a series circuit. When we take the voltage rises and add them to the voltage drops, the total sum is 0. When we take the total current in parallel and add it to the currents, we have a sum of 0. The current entering plus the current exiting equals 0. Or if we put the current entering on one side and the current exiting on the other side, entering, exiting, they will be equal. So this is where you have I total equals I2 plus I3 plus I4. And that could be a little confusing. We can change that to 2 and 3 to be following what we talked about. So I total equals I1 plus I2 plus I3. So if we look at this, this representation here of this equation, but using E and R, this is another means or ways of proving our total opposition equation. So this is equal to I total. I total is equal to the sum of each branch current. And each branch current is being represented here as E over R. So this is I1, this is I2, this is I3. We know I total is equal to the sum of all those. So this is the same equation as the current being represented as E over R. And now all we have to do is remove the common quantity of E, or voltage, from each one of these terms, and you would get this as a result. And now if you just remove the reciprocal from here and bring it over here, you have 1 over R1 plus 1 over R2 plus 1 over R3. Resistors in parallel. So purely parallel circuit analysis is actually really quite simple. And that is, when you're looking at each and every branch, it's just a simple series circuit of which Ohm's law will give you the total current in that branch. And because it's all connected to the same source, the total current flowing from that source is simply adding up each and every series circuit that was connected to that source. So if you look at this, we've got branch 1, a simple series circuit with one component. Branch 2, another series circuit connected to the same voltage with its current. And branch 3, and so on. So when it comes to calculating these currents, we know that our source voltage is the same as our VR1. So source divided by R1 gives you your branch 1 current. We know that ES is equal to VR2, so we know that our source voltage divided by R2 gives us our I2 current, and so on. Right? You can see how, in this case, all the branch currents are determined by simple Ohm's law of E over R. I total, likewise, can be determined by our source voltage, same voltage, divided by the total resistance that's calculated for the parallel connection. So if we take this example here, we can look at our first branch where we have 45 volts, our second branch where we're going to have 45 volts, and our third branch where we'll have 45 volts. Purely parallel, sharing the same two terminals of the source. They have the same voltage across them. Ohm's law will calculate the current based on E over R for each and every branch. So I total equals ES over R total. Remember, this was the R total value we had. And so when we divide that R total into our source voltage, we get 6.67 milliamps. And now we look at the individual branch currents. I1 equals E source divided by R1, which equals 803.6 microamps. I gotta just calculate that. Is that microamps? 45. And so that's 803.6 microamps, and for some reason the engineering prefixes are not coming through when I bring up this presentation on my iPad. So we just added that in there. And so we've got microamps, we've got milliamps, just adding the equal signs. And so now, to confirm our Kirchhoff's current law, we're adding this term to this term to this term, and sure enough we get our total current, which is what we have here. So E source divided by R total gives us our total current, or adding all the currents together gives us the same result. So it's a way of verifying. But you can see how simple it is, where just each and every branch is a series circuit with a single load. And so you just calculate the current using Ohm's law and add it all together. So power dissipation in a parallel circuit, all of our power relationships apply. So V times I, of course, I squared R, or V squared over R. And the total power is just like any other circuit, where if you have the individual powers, you just add them up to give you total power. And this is good for any circuit. It doesn't matter whether it's series or parallel or a combination series parallel circuit. If you have the individual powers dissipation of each device, you just add them together to give you the total. Now in parallel, there's, of the power formulas in parallel, there's two that are used regularly because of how direct they are in determining our power value. So as an example, V times I. If you know the current being drawn from a source, just multiply the two together to give you power total. Furthermore, if you're wanting to figure out the power dissipated by any resistance in parallel, what you have to do is just look at the V squared value, which will be the same for each and every resistor, right? So if you've got parallel resistance, R1, R2, and R3, and you know the voltage is the same across all of them, voltage, volts, then the V squared value is going to be the same for each one of these. And so this becomes a quick and efficient way of determining power dissipation or individual power dissipation in a parallel arrangement. So just a review of Kirchhoff's current law. I think we got that now. I1, I2, I3. So let's look at how that would be applied to examples here of current entering a node and exiting a node. So here we can see by the arrows, this is something called a node. So it's no longer a point. A point is a point of reference in a circuit for voltage, where there's one input, one output, and a node can also be a point as well. But here, this is definitely a current division node when we look here, because we've got current entering and then we've got current being divided into three exiting paths. So notice how here the current entering is described as I1, which we know has to equal the sum of the current exiting. So I2 plus I3 plus I4. At junction B then, the current entering the node is I2 plus I3 plus I4. And the current exiting the node is I5. We know that this is what's called balanced nodes, where every node is balanced for current. Current entering equals current exiting. So let's take a look here then. If we look at this current entering this first node here, that would have to mean there's 9 milliamps exiting. If we look at that 9 milliamps exiting, and then we look at everything that is going to be concentrating on this node, we can see 9 milliamps entering. We can see a total of 6 exiting here. Whoops. What the dickens? Okay, we can see a total of 6 exiting here, a 2, plus a 4, and now that leaves one exiting node here of 3 milliamps. And now we have to see if that all balances with this last node. So you've got 3 entering, 1 entering, and 4 exiting. So that means you've got 1 plus 3 equaling 4. So we can see we have balanced nodes. Okay, here's where we see an example of where we have a reference arrow for I3. It didn't ask you if the current was entering or exiting. It's simply representing I3 as an arrow in that direction. And what this is an example of where once you're given a reference arrow for I3, if the actual current is in the opposite direction, you're going to indicate that by the use of a negative sign. If it's in the same direction, you don't provide a sign or you call it plus. But if it's in the opposite direction, you give it a negative sign. So let's take a look here. If we look at what we have as 2 amps entering and 3 amps exiting, we know that would have to mean if there's 3 amps exiting and 2 amps entering, the only way we can balance this node is to say that there's 1 amp entering. to balance that node. Notice how the actual direction of current is opposite to the reference arrow, and that means that I3 would have to be shown as minus 1 amp. And we show it as minus because the actual current direction is opposite to that of the reference arrow given. So does that balance this last node? Well, we should. We know that that's 1 amp exiting. So this is 1 amp exiting. This is 6 amps exiting. And notice how this reference arrow is showing current as if it's exiting. Well, we know that our actual current is 7 amps entering that node in order to balance it. So that would mean I5 would have to be expressed as minus 7 amps. Okay, let's take a look at this one then. There's a number of different approaches you could take to this one. We don't always work from the left to the right. We have to see what information we're given and then work with it and work on balancing each node. So in this case, we could start at the far right and we could say, so we've got 10 amps exiting, we've got 2 entering, 3 entering, for a total of 5 entering. That means the missing current has to be 5 amps. This is now a balanced node, 5, 3, and 2 entering and 10 exiting. Over here then, we know that we have to have 10 amps entering that node in order to balance it. And therefore, with 3 amps entering here, the remaining current is 7 amps entering here. If we look at balancing 7 plus 3 equals 10. 10 equals 5 plus 3 plus 2. 5 plus 3 plus 2 entering equals 10 exiting. So take a look at this one. I'll give you a little bit of time to look that one over. So one way to start this is, let's suppose that inside this box is essentially a single point, which it is. As far as the source goes, this is a single current division node of where I have 24 amps entering. I have 24 amps entering. I have it exiting over here. So we know current entering has to equal current exiting. So this means that I7 would have to be 24 amps. Okay, so now we have I7 exiting. That means you've got 6 amps and 5 amps, and I5 entering. So that means the result is going to have to be 24 minus 6 to give you I5. So that means that's going to have to be 18 amps. With this being 18 amps and this being 11 amps entering, we know that I4 then has to be the remainder of those amps, and that's going to have to be 7 amps. So 11 plus 7 gives us 18. Now, if you look at the 7 amps exiting here and the 6 amps exiting here, that means there's got to be 13 amps entering. And notice how 11 plus 13 equals 24. So if we were to imagine a source voltage over here as an E total value with a positive and negative terminal here, the current leaving the source has to equal the current returning to the source. And that's where we can start with this analysis or balancing these nodes. So in series, we had the voltage divider rule. In parallel, we'll have the current divider rule. A series circuit is a voltage divider, and a parallel circuit is a current divider. So how do we go about coming up with our equation for current divider? Well, one of the ways to look at it is when it comes to resistance and voltage, we have a direct relationship. So in a series circuit, the greater the resistance, the greater the voltage. So in the current divider rule, it was the greatest resistor, or the largest resistor, that had the largest voltage drop. When we're looking at a parallel circuit, current and resistance are inverse, aren't they? The largest resistor connected in a parallel circuit is going to have the smallest current. It's the smallest resistor that's going to have the largest current. So there's an inverse relationship. And so what it means is the fraction that we use to calculate the division is inverse to what it was for the voltage divider. So if we look at going through this as coming up with the current divider rule, what's missing again is the equal sign. So we can say that E source equals VR1 equals VR2 equals VR3. We know that voltage is all the same. Voltage is same in parallel. Okay. We can also therefore say that ES equals I total times R total. Makes sense, right? Ohm's law, IR. We can say that VR1 equals I1 times R1. VR2 is I2 times R2. And VR3 is I3 times R3. Because we've got our value of I total times R total equaling VR1, that means that has to be equal. That means this has to be equal. And this has to be equal. All we're saying is E source equals each one of those voltages for each branch. Remember, branch 1 voltage can be represented this way, branch 2 voltage can be represented this way, and branch 3 voltage can be represented this way. And those voltages are all the same. And they're therefore equal to I total, R total. So what does that look like when we look at a current divider then? It means that I1 will equal the fraction of R total versus R1 multiplied by I total. Notice how this is the fraction inverse to what it was for R1's voltage in a voltage divider. Okay, I2 equals R2. I2 equals R total over R2 times I total. I3 equals R total over R3 times I total. The fraction is inverse of what it was for the voltage divider, and it's all proved by just flipping this equation around to give you this, flipping this around to give you that, flipping this around to give you this. So this is called the current divider rule. Okay, so when it comes to this example here, we can use the current divider rule to give us our branch currents in each one of these examples. Notice how the first thing we did was determine R total, right? How would we come up with an equation for branch 1? I1 would equal R total over R1 multiplied by I total. So how would I total be calculated? Well, we would take our I total would equal E source divided by R total. So picking up on this example, we've got our R total value here given as this calculation. We have our I total value here. So we already have I total. We can use the current divider rule to figure out the individual branch currents. But I would also say that based on this equation here that I gave and the fact that you have I total and R total now, you could simply calculate an E total value of equal to I total times R total to give you a value of applied voltage here. And once you had the value of applied voltage, each branch current would be very simple. So I1 would equal E total divided by R1, I2 E total divided by R2, and I3 would equal E total divided by R3. And of course that's a way that you could verify the calculations using the current divider rule in this next slide. So as usual, the equal signs and operations are missing here, but let's just add them. I1 equals R total over R1, that inverse fraction, because we have an inverse relationship between current and resistance. I2 equals R total over R2 times I total. I3 equals R total over R3 times I total. So this is the process of going through the calculation to get each one. And when it comes to these branch currents, each one could be confirmed as I1 equals E source over R1, I2 E source, the same value as I1 of course for E source, over R2, and then here I3 equals E source over R3. Okay, Kirchhoff's current law says that adding the currents all together will equal the total current. So next we're going to look at the faults, the effect of faults on parallel circuits. And one thing to note right now is that when it comes to faults in a purely parallel circuit, we never investigate a short circuit. And the reason being is because when we're talking about a short circuit in a parallel circuit, the theoretical result would be infinite current. So in a calculation, you would conclude that you have infinite current, but then the issue always comes down to, okay, with infinite current, what would the ideal source be? And the ideal source, you would say, can supply infinite current while still providing the same voltage. So because it's impractical in nature, and a practical circuit would certainly, upon seeing infinite current being drawn by the circuit, would cause overload protection to come into place, because we know that our source can't handle infinite current, our practical source can, our conductors cannot, and our loads cannot. So just by principle, we don't look at the effects of a short in a parallel circuit, with simply the understanding that should it be a practical circuit, like what we're studying, when you have a short in parallel, like a short on one of your receptacles in your home, what happens? The breaker trips, you have to remove the short before you can restore the circuit and enable the breaker again. So that's really what we're talking about here, and we're looking only at opens when it comes to a parallel circuit. So if we look here, if we look at this circuit to begin with, let's just suppose it's three parallel connected loads of all of the same power capabilities or power ratings. That would mean that each one, when connected to the same voltage, would be all the same resistance. Right? So if we started out where we had 12K, and 12K, we know that the R total value, when we have three resistors in parallel, is the value of 1, 12K, divided by the number, of resistors, in this case 3, and we already calculated that earlier as a 4K ohm total resistance. The thing we need to understand in a parallel arrangement, when we remove resistance, that is when we remove one of the paths for current to flow, we end up with a greater resistance or a greater opposition. And that's reflected in that inverse current and opposition relationship. If there's less current, there has to be more opposition or more resistance. So removing a path causes the resistance to go up. And we can see that when we look over here, because now we have no presence of intermediate branch or a middle branch here, and we're only left with branch 1 and 3. And therefore that means the R2 value is not part of this equation anymore, and you only have R1 and R3. Here we could use product over sum, and you could say that's 12 times 12 over 12 plus 12 as a value in K, gonna give you 6K ohms. Clearly 6K ohms is more resistance than 4K ohms, and this is our new R total value. And if we look at the individual values of opposition, we have 50 volts of applied. Our individual value of opposition is 12K for branch 1. Infinite ohms for branch 2. Therefore, it's a branch that is no longer connected or part of the opposition. It's like it was removed from the circuit. And you have R3 as 12K. So total opposition now is greater than it was and is a total of 6K ohms. So we calculated the individual branch currents before of 4.17 milliamps per branch. So we had I total equals ES divided by R total. We have I1 equaling I3 equaling I total divided by 2. So each one of the branches, I1 and I3, is equal to 4.17 amps. I total is going to be 50 volts divided by 6K. I2, where we have the infinite ohms of resistance, is going to be a 0 amp current, and therefore we just have 4.7 times 2 as our total current. So this is going to be I total was equal to 4.17 milliamps plus 4.17 milliamps, which was equal to an I1 plus an I3, because of course I2 is 0 amps. So notice that when we have an open in a purely parallel circuit, R total goes up. Remember, R total went from a value of 4K to 6K, so I total goes up. We have an inverse relationship between opposition and current, and therefore I total went down. When it comes to I1 and I3, they were unchanged by the open branch. We still had a value of I1 that was determined by E source divided by R1, and a value of I3 that was E source divided by R3. That didn't change. We still had source voltage across them. They still had the same resistance. So I1 and I3 stayed the same or were unchanged. And this is how we have independent load operation of your loads within your home, because they're connected in a parallel arrangement. If any one of the loads is broken, disabled, open, or even a switch turned off for that load, the remaining loads within your home still have the source voltage and are still doing the same amount of work and dissipating the same amount of power that they always did. They were independently and unaffected by another load within the circuit, within the purely parallel circuit. Okay, so let's take an example of this guy, and let's use the peer table from what we used in our last example. So take this peer table, apply it to this, and put in the known values, and then we will look at it together as to how we can apply parallel circuit properties to the peer table now. So I added my known values to the peer table. I added the total power value given as 2.56 watts. I added the total current as 80 milliamps. And then I added the individual branch currents of R2 and R3. So those are my known values. And now, based on the fact that we have a parallel circuit, we know a few things can be applied to this table. One of them being that when it comes to our current, each one of these branch currents have to add up individually together to give us our total current. That's Kirchhoff's current law. So we can apply Kirchhoff's current law to this row of the table. Up here, we know that E source equals VR1 equals VR2 equals VR3. So that means once we have a single value of voltage, we can fill it in all the way across the table. So then to start with, and applying purely parallel principles to this, we have two things. One of them is we have two values within one column. And we know that that is enough to determine an unknown value. And so when it comes to working down in the table, we can do a division. So that means in this case, we can take our 2.56 whole units of watts and divide by our 80 exponent minus 3 amps in order to give us our value in volts. And in this case, it's 32 whole units of volts. Knowing that we have voltage all the same in a purely parallel circuit, that means we can put 32 volts all the way across. Okay, so having 32 volts all the way across is going to allow us to determine really all the remaining of the values of our purely parallel circuit, right? So let's take a look at this last remaining current. When we look at adding the 12 milliamps to the 36 milliamps, that's going to give us 48 milliamps. So if we take our 80 milliamps of total current and minus 48 milliamps for the branch 2 and branch 3 current, that's going to give us 32 milliamps as our unknown current. From there, then, you can work down by division to determine each one of your branch oppositions. So branch 1 is going to be 32 volts divided by 32 milliamps, which is going to be 1 k ohm. Then you move on and you go 32 divided by 12 exponent minus 3 to give you 2.67 k ohms. And then you're doing your last one, 32 divided by 36 exponent minus 3 to give you 889 ohms. And then from there, you can go about you can go about a division here to quickly determine your parallel resistance. Now, of course, what you could do is apply the sum of the reciprocals for each one of these, and you would get the same result. So 32 divided by 80 exponent minus 3 is going to give you 400 ohms. Now, if we look at evaluating this total resistance, what are we going to do? We're going to look at it to be less than the smallest individual value here, and we can see that it's clearly less than 889 ohms. Then from there you can just calculate your powers. It's just a multiplication, isn't it? So 32 volts times 36 gives us 1.15 watts. Then we can go to the next one, which is 32 times 12 exponent minus 3 is 384 milliwatts. And then the last one, 32 times 32 exponent minus 3 is 1.02. Now, if you were to add those all up, you should be able to confirm that the power total value is the sum of all the individual powers. So let's try that. 1.02 watts plus 0.384 watts plus 1.15 watts. And sure enough, you get 2.56 watts. Okay, so what if R1 opens? Okay, so now let's go back to our completed circuit when it's operating normally, and we're going to look at the result of R1 opening. But before we go there, what's the property of R1's opposition when it opens? R1 would now equal infinite ohms. What would be the value of R1's current? IR1 would now be 0 amps. So knowing that, then we can take that back to the peer table. So here's our table previously, and if we look at what we have here in terms of our values and the fact that R1 is now open, what it means is that with R1 open, we're no longer going to be seeing for that branch, the R1 branch, the opposition of 1K. So we have to get rid of that. That's gone. We have to understand that its branch current, which was 32 milliamps, is now going to be what we know is 0. But we're still going to have across the open circuit the 32 volts of applied voltage. It's an open circuit. So we're still going to have present the potential of the, essentially the power rails from the source are going to appear on that branch. It's just like when the lamp burns out in your home, there's still voltage present across the lamp. There's just no current through it because it's gone open. So is the lamp doing any work anymore when it's gone open? No, it hasn't. So therefore we have no longer any power, right? So now in each individual branch is going to be unaffected, isn't it? R2 is going to be doing the work it always was. R3 is going to be doing the work it always was, but total values will not be what they were previously, right? So this is how the table is going to change, is by what we see here. So now if we look at the new values then and add them, let's look at R1, the R1 branch. Power now is going to be 0 watts. Current, we know it's going to be 0 amps. The resistance is going to be infinite ohms. If we look now at the total values, we know there's still going to be 32 volts applied to the circuit. We know that now our current is going to go down because we're missing branch 1's current, and we're only going to be looking at the current of branch 2 and branch 3 to give us a total of 48 milliamps. Our powers now will just be the result of P2 plus P3. So we'll look at adding those up. 0.384 watts plus 1.15 watts to give us 1.53 watts. And now we can do a division to determine our total resistance. And when we get our total resistance, remember, we should be expecting it to be less than 889 ohms. So that would be 32 divided by 48, exponent minus 3, to give us now a new opposition for the total circuit of 667 ohms. And notice how that's considerably more than what we had previous, where we had 400 ohms. So notice how we took a fault as an open within the parallel circuit and looked at its new values, and based on missing branch 1's current, we had less total current, less total power dissipated, and more resistance, or more R total. Okay, so that's it, and we will publish this and then do the practice questions at the end of chapter 6 as assigned on D2L. All right.